Okay, so last week we were talking about acceleration, and as an aside, tomorrow's quiz will be on acceleration. Okay, 2 acceleration problems because we're just starting work energy theorem today and probably won't get far enough into it to be worth testing tomorrow. Okay, but acceleration relates to work energy theorem because of this. If I want to cause something's velocity to change, what do I probably have to do to it? Yeah, I either have to give it energy or I have to take energy away from it. Okay, one or the other. The very first day of this unit, we talked about what mechanical energy is. Okay, mechanical energy, okay, is the sum total of an object's kinetic and potential energy. Okay, kinetic energy has to do with how fast you're going, and potential energy has to do with either your position, that is above the ground, or your condition, that is if you're elastic in nature, you are stretched or compressed and have the potential to go back to a different shape. Okay? So if I cause something to accelerate, then I'm going to change its velocity, either positively or negatively. If I want it to go faster, I would probably have to add or subtract energy.
Add.
Okay. If I add energy, what I have to do is I have to exert a force on the object. And I have to do that over a distance. Okay? And if I multiply those two things together, what I'm doing is work. Okay? That definition was also in the first day. Work is a change in mechanical energy, or a transfer of mechanical energy. Okay? Heat was a change or a transfer of thermal energy. Work was a change or a transfer of mechanical energy. Okay, is that ringing a bell from the other day? I know it's a long time ago now, but. Okay. So if I want to change the mechanical energy of an object, either the potential energy or the kinetic energy, then I have to do work. Okay, I have to exert a force through a distance. So, if, normally I would put this on the floor, but I'm not flexible enough today. Okay, so my water bottle is on the chair. Okay, if I pick it up and put it here, have I done work?
Yeah.
Why?
Because a force to lift it over the distance of the chair to the top.
Right, and does it have more energy there?
Yeah.
Yeah. Okay, it has more of what kind?
Potential.
Potential, and thus more mechanical. Okay, so it has more potential energy. The only way you get more energy is if something or someone gives it to you by doing work. Okay, so that's the idea of the work energy theorem. Okay, work energy theorem says that work is a change in energy, in particular mechanical energy. So what we will do throughout the rest of this unit is we will be using this formula, which does not ever appear in that form on your formula sheet. It appears in 2 separate forms on your formula sheet. It appears like this, and it appears like this. But if work equals both of those things, can I say that those things equal each other?
Yeah.
Okay, so what we'll be doing a lot of in this part of this unit is setting force times distance equal to the change in energy. Okay, and then solving for, what the velocity of, or what the speed of the object will be after work is done, or what the height of the object will be after a set amount of work is done, those kinds of things. Okay, it's going to be mostly algebra, okay, but we do have to understand the connection between what we do, force and distance, and what happens, the change in speed or the change in height. Okay. All right, now, if I exert more force, will I do more work? Yes. If I exert the same amount of force, but I exert it over more distance, do I do more work?
Yes.
Yes, because both of those things linearly relate to work. Okay? If I exert twice as much force over the same distance, I do twice as much work. Okay? Everybody all right with that idea? Okay. simple example of work energy theorem. Okay? The operation of the basic mousetrap. Okay? How many people have ever used one of these before? All right, good. None of you put out poison. Okay? Poison is cruel. This is quick. Okay? So, in order to set a mousetrap, what do you have to do?
Pull the thing back and then put like the thing will go so that it's.
Pull the thing back and then put the thing in? Okay, yeah. All right, so the technical terms for all of these things are, okay, that this is the spring, this is the trigger, this is the trigger bar, and this is the killing bar. That's its name. Aptly so, because that's its job. Okay, it snaps the little neck of the mice. Sorry, guys, but that's much more humane than poison. Okay,
Poison kills more.
but poison will kill more of them. But the other problem is, people's pets sometimes give in to the poison. That can be a problem. Okay, and it's slower. It's not as humane. Okay, so with this, okay, when I pull the killing bar over, okay, to its loaded position, what am I doing to the spring? I'm giving it potential energy because I'm changing its shape. It's elastic in nature. Okay? It wants to go back to its original shape. Okay? So when I pull the killing bar over, I exert a force through a distance. Have I done work? Is that energy now stored in the spring? Okay. When the mousetrap is triggered, will that potential energy be released? Okay, what will it be turned into? Yeah, kinetic energy. What else?
Mechanical energy.
Well, it's actually already mechanical energy, because if you have either potential or kinetic, you have mechanical, but you're changing the type of mechanical by changing it from potential to kinetic, definitely. Okay, will it become any other kinds of energy?
Sound and heat.
Sound, heat, okay, death. Okay, yeah, it's going to change the shape of the mouse. Okay, that counts as work. Okay, if your finger was in there, it would change the shape of your finger. Okay, that's work. All right, it counts. Right, any change in shape is still a force exerted through a distance. So, okay, yeah, it would be converted into other forms of energy. If this was a perfect world, would all of that energy be accounted for?
Yeah.
Yeah. Okay, if it was a perfect world, it would actually all become kinetic. We wouldn't hear it. Okay? There wouldn't be any sound. Okay? There wouldn't be any heat or anything like that. Okay? All of it would be converted to kinetic. Obviously, in the real world, there are wasted forms of energy like sound and heat. All right. Okay, so definition here, an important one for you to know. Okay, work is the transfer of energy from one object or system to another. Okay? And energy is the ability or capacity to do work. Okay, so if I'm holding a brick, okay, above my feet, it has potential energy, because if I drop it, it will,
Hurt my feet.
it'll fall and then hurt my feet. Okay, so energy is a measure of, or is the capacity or ability to do work, and work is a transfer of energy. So does that seem like a chicken and the egg problem?
Yeah.
It's not, though. Just like the chicken and the egg question is not a real question.
Egg came first.
Egg came first. Birds evolved from reptiles, and reptiles lay eggs. I think we've had this discussion before. Okay, so eggs definitely came first. Okay, but also, can you do work if you don't have energy? No. Okay, so energy has to be present in order to be transferred, okay, to something else. Okay, so if you wake up in the morning and your parents say, "Oh, go out and shovel the driveway," you're like, "I don't have any energy." You're lying. But if you actually had didn't have any energy, you would also be completely incapable of shoveling the driveway. Okay, because shoveling the driveway is work. Okay, you move the snow around. Okay, you give it kinetic energy, you pile it up, you give it potential energy. Okay, you're taking it from the driveway. Okay, that's work. All right. questions on those two definitions? Those multiple choice question kind of things? Definitely. Okay, so much research has gone into applying work energy theorem to practical situations. One of the best places we see that is actually sport science, in particular in the development of equipment and technique. Right? If we're looking at this diagram here, which is like a stop motion diagram of a tennis serve, okay, what are some things that would be important for influencing the speed at which you can serve the ball? How fast you can move the racket. So that would be the force you could exert on the racket. Okay, what else? Is the amount of work you do going to influence the speed of the ball? Okay, what's the other part of work? Force and distance. Okay, so work energy theorem says the speed at which you serve the ball is a function of two things: how much force you can exert and the distance over which you can exert it. This is part of the reason why tennis rackets are rackets and not paddles. Otherwise it would be pickleball, which apparently now has a professional league. I saw on the weekend. I'm like, oh my God, I thought that was just a sport for old people. Okay, but apparently it's not. Apparently young people play it competitively as well. So, with a tennis racket, okay, why do we want it to be a racket with strings and not a paddle?
Strings are bouncy.
Strings are bouncy. Part of the reason?
It lets you move it quicker because there's less resistance.
Yeah, it lets you move it quicker because there's less resistance and it has less mass. If it's a solid paddle, it's going to be heavier. Okay, which is why pickleball, as I found out, is far less exciting to watch than tennis, which I can't say is much more exciting than paint drying, but okay, it is, a little bit more exciting because the ball does move significantly faster, right? Plus, a tennis racket is also longer. Okay, so you get a longer lever, which helps your force. Okay, now, so the length of the racket is fixed. You can only, in tennis there are rules around the length of a racket. Okay, it would be an unfair advantage if you had a 4-foot long racket. Okay, so the force you can exert is essentially fixed by your strength. Okay, so yes, part of serving a tennis ball fast would be training your muscles to be stronger so that you can swing the racket faster. But the other part of that equation is the distance over which you can exert that force. This is where the springy nature of the string comes into play. When that ball hits the racket, so this is the frame of the racket, when the ball makes contact with the racket, it stretches the strings out, behind the racket, which means that the ball stays on the racket over a longer distance than if the racket were a paddle. If the racket were a paddle, the ball would deform against the paddle and bounce off of it very quickly. Okay, that sort of makes sense? Okay? Since the nature of a tennis ball is fixed by the rules, every tennis ball compacts the same amount against the strings or the paddle. Okay? So, modifying the way the racket works could give you a greater distance over which you could exert your force, or improving your technique. Okay? If that ball gets out ahead of you a little bit because you don't throw it perfectly straight up and you're leaning forward too much, do you get it against the racket for as long? Then you don't hit it as fast. Okay? But if you get it straight over your head, you're going to be in contact with it for a greater distance, which means you will hit it faster. Okay? That sort of making sense? Hockey sticks, same thing. Okay? When I was a kid, a hockey stick was a chunk of tree. Okay? They were wood, they were heavy, they weren't terribly flexible. Okay?
Those are the type of sticks I used.
Well, but now you get these carbon fiber graphite things that are like a wet noodle. Okay? Like you see somebody back in the, let's say the 80s, I'm not going to, or the 70s, okay? And a wooden stick can flex through an arc about like that. It's not terribly flexible. Okay? You see now guys doing a one-timer in the NHL, okay? And that stick goes like this. Okay? Sometimes it explodes. Okay, like, you know, when you're just about to have Leon Draisaitl score a goal and the stick explodes and, you know, the bad stuff happens. Okay, but having that stick be more flexible means that now that well-trained, strong athlete can exert that incredible force over a much greater distance. Does that mean they shoot the puck faster? Okay, so it creates an advantage, right? Equipment gets better, right? Golf clubs, same thing. Golf clubs are designed now, instead of having steel shafts, they have graphite shafts. They're more flexible. They've changed the design of the ball. Okay? Hitting a golf ball 40 years ago was like hitting a rock. Okay? Now the balls are soft, so they deform and they flatten against the face of the club, and they stay on the face of the club over a greater distance. So now instead, 40 years ago, if you could hit the ball 280 yards, you could really hit the ball. Now, if you don't hit the ball 400 yards, you can't get to the green in 2. Okay? So it's gotten that science has made use of work energy theory. Okay? It's also useful in protective equipment, padding and helmets and all of that. Okay? If we can increase the distance over which your head is slowed down when you get crashed up against the boards, okay, you are less likely to suffer a concussion. Okay? Your head's velocity will change over a greater time. Okay? Car safety equipment, same idea. Okay? Seat belts, airbags, all of that stuff. Crumple zones. Okay? That making some sense? Okay? So there's a lot of applications for work energy theorem. About the only sport that hasn't embraced this is baseball. Okay? Baseball still involves throwing a chunk of horse at a piece of wood.
Probably because if you made it easier, everybody would get touchdown. Everybody would get home runs all touchdown.
Well, maybe what I'm saying isn't entirely true. Baseball hasn't embraced one type of science. A lot of roid monkeys in baseball. A lot of steroid use in baseball. Or corked bats. Have you ever seen when Sammy Sosa got busted for having a corked bat? It's like one of the greatest sports cheating exposures ever. So what he would do is he would drill out his bat. Okay? And he would fill it with cork. What advantage does that serve? Makes it way lighter. And this guy was a big, roid-infused guy. Okay? And he could swing that bat really fast. The only problem with corking your bat is it does somewhat
break.
Yeah, make it less structurally sound. Okay? Because it's now a hollow chunk of tree instead of a solid chunk of tree. And your Louisville Slugger is now a Louisville Noodle. Okay? And the problem is you cranked the dinger with it, and the bat exploded. And when the umpire went out to pick up the pieces, he's like, this bat is hollow. You're a cheater. Okay? And then, so you didn't embrace that. Lighter bat, swinging faster. That affects this part. So does the steroid part. That affects this part too. Okay? Some part of the work energy theorem, okay, still being embraced there. Okay? Does that make sense? Okay. All right. So work is related to force. The more force you can exert, the more work that you can do. Okay? Mass also affects the amount of work done, as a more massive object is going to require more energy if you want to change its speed or change its height by the same amount as a lighter object. Okay? So, the prime example, or the perfect example, and we'll come back to this and do lots of questions on this, is a bow and arrow. Okay? When I draw back a bow, do I have to exert force?
Yeah.
Okay. Through a distance?
Yeah.
Okay, what kind of energy is in the bow?
Potential.
What kind?
Mechanical.
Elastic, right? The bow wants to go back to its original shape. There's tension in it when we draw. When we draw back the string on a bow, what we're doing is pulling the two ends of the bow together. Okay? That stores elastic potential energy inside the bow. In the perfect physical world, okay, if I then release that bow, let's say I've done 100 joules worth of work in drawing it back. When I release the bow, how much energy will the arrow have?
100 joules.
100 joules. Okay? Because I did work and put potential energy in the bow. When I release the bow, I let the bow do what? Work. It does work on the arrow. Transfers all of its energy to the arrow, and the arrow flies up. Okay? That's a work energy theorem type of situation. Okay? I tell you how much force I exert and over what distance, and I ask you what speed the arrow will leave the bow at. Okay, so you would then have to understand that, okay, Mr. Corderi did work and I have the force in the distance, okay, so I would have this and this, and I'd be changing what kind of energy about the arrow. So if I pull the bow back and then I let it go, what's going to happen to the arrow?
It's gonna go to the kinetic.
Yeah, the work I did, which was potential energy in the bow, is going to become kinetic energy in the arrow. So if I'm just talking about the arrow's kinetic energy will change. Remember, delta means final minus initial. Okay? How much kinetic energy does the arrow have sitting in the drawn bow? 0. It's not moving. Okay? But all the energy's in the bow. The arrow has nothing. Okay? The arrow is just in the bow. Okay? It's not moving, it has no kinetic energy. But as soon as I let go of the string, okay, then the string will push on the arrow, okay, and the arrow's kinetic energy will go from 0 to some other number. Okay? That other number would be however much work, we said 100 joules, was done on the bow. Okay?
But
As long as I knew the mass of
friction
the arrow.
itself.
But again, we're only dealing with the perfect physical world. So we're never going to have to worry about how much energy is lost to sound and heat and all of that. Okay? So if I knew the mass of the arrow, I'd be able to calculate the speed the arrow leaves the bow at. Okay? That's how all of our work energy theorem questions are going to go. There's either going to be a change in kinetic energy, or there's going to be a change in potential energy. Okay? So there'll be a little bit of algebra, but it's not terribly difficult. Okay? All right, now, this has to do with acceleration and force. So this is Newton's second law. Okay? So it's more about kind of the effect of mass, okay, on acceleration. So I have the golfer there, and he's set up in a normal situation where he's going to hit the ball. Okay? He's going to swing as hard as he can, okay, and hit the ball, which has an incredibly small mass. That should produce an incredibly large what? Acceleration. Okay, and the ball will take off. Now, for whatever reason, he wants a challenge. So he's going to wind up and smoke that truck. Okay, so same amount of force. Okay, but now he's hitting a colossal mass. What's going to happen to the acceleration? It'll be minimal. Yeah, it'll be very small. Now, if that truck is sitting on a frictionless surface, will it move?
Yeah.
Yep, absolutely it would. Okay? What if it's not sitting on a frictionless surface? Okay, so it doesn't move. Does that mean it doesn't accelerate? Nope, it doesn't mean it doesn't accelerate. Okay, will he leave a dent in the back of it? Okay, does part of it accelerate then?
Yep.
Okay, here's more evidence of acceleration. If I'm standing at the front of the truck and I have my hand on the front of the truck, will I feel when he hits it? The vibration will travel through the truck, yes?
Yep.
Does that mean every single particle in the truck moved?
Yep.
They just didn't move together. Okay, but that was transferred through the truck. Okay, so work would still be done because there would still be evidence of an acceleration of some kind. Be a lot more difficult to calculate. We would deal with a situation like that. Okay, so motion doesn't have to mean that an object actually moves from one place to another. It could just mean that I change its shape. So stretching a spring, a bungee cord, a rubber band, okay, or something like that still counts as movement. A change in shape, like a dent in the truck, okay, still counts as movement. Okay, so with a spring, or any elastic object, you can generally do work, okay, by stretching it or compressing it. Okay, a rubber band, that doesn't work really, okay, because the rubber band is just designed to be stretched. Okay, but if you had like a chunk of rubber, you could compress it or stretch it, okay, and it would take, it would absorb or require potential elastic energy in either direction. Okay. All right. Okay, this we talked about before, but I just wanted to review it. Work and heat are both transfers of energy, but they transfer different kinds. Okay? Work is a transfer of mechanical energy. Heat is a transfer of thermal energy. Okay. All right. All right, so potential energy, okay, is energy, we said, due to position or condition. We're not going to deal very much with calculating elastic potential energy other than by using force times distance. We're not going to deal with Hooke's law and things like that in Science 10. Okay? We're going to deal mostly with gravitational potential energy.
There's so many hooks inside.
Whoop, sorry, that's not right.
It's the same other Jackson.
Okay. You remember Hooke? Hooke's the guy who invented the microscope? That Hooke.
Wait, the same
Okay?
dude, yeah.
Same dude. I told you, he's a physicist. He only handed biology their most important tool ever.
I was just
Okay?
making fun
His
of
physics is
how
awesome.
I was just making fun of how everybody had the name Hook.
No, same guy. Okay? His physics is awesome, and he came up with all kinds of great things. Okay? All right, so potential energy, gravitational potential energy, is dependent on three things. Okay? What do you suppose those three things might be? Gravity, absolutely. Okay? Acceleration due to gravity. Right? We abbreviate that with a little g. And that little g is this number that we learned last week. Okay? If we're on Earth, or somewhere else, it'd be a different number. Mass, absolutely. Okay? I mean, think of it this way, guys. There are two objects falling off a building towards you. One of them is going to hit you, but you have a choice. Okay? One is a piano, and the other is a tennis ball.
Tennis ball.
I picked the tennis ball. Okay, now if you're kicking the piano, we'll talk after class. Okay, I'm worried about you if that's the case. Okay, but the tennis ball would obviously hurt me a lot less because even though they both fell off the same building and they're going to be going the same speed when they hit me, the tennis ball is going to hurt me a lot less because it has less mass. Okay, mass affects how much work you can do. Okay, I mean, what would you rather get in a head-on collision with? A kid on a tricycle, okay, or a semi-truck?
Tricycle.
Okay, a kid on a tricycle, they have less mass.
Sorry, tricycle kid.
Okay, like, I'm not saying you're going fast. I'm not saying you're in a car, you could just be walking, okay? Definitely the kid on the tricycle, you just reach out and stop them, okay? They don't have enough energy to hurt you. The truck, don't reach out like this, get out of the way, okay? That's not gonna end well. All right, and what's the last thing you spoke? Height, yeah, okay? The farther it falls, obviously the faster it's going to go, so the higher something is, the more potential energy it has. Now, we do have to remember, though, potential energy is just that, potential. It can't do anything until it's converted into what? Kinetic, okay? Like right now, sure, this water bottle has the potential to fall, but it's not going to do anything until it does. Okay, so potential energy isn't going to do any work until it can be converted into a type of energy that can. Okay. All right. So yeah, Wile E. Coyote, the guy that never falls until it's pointed out to him that he's not standing on anything anymore, right? You guys seen Looney Tunes before? Yeah. Okay, so gravitational potential energy and work. This diagram here. These two blocks have the same mass. One person lifts the block to the top of that ramp. The other person pushes it up the ramp. The ramp is frictionless. Okay? They push it up the ramp to the top. Who does more work?
Because one's over a longer distance.
They both do the same amount of work.
I was right.
Yep. Come back to this, guys. Work's a change in energy.
If the ramp is frictionless, how do you go up it?
Good question. You have magic shoes.
Because of the way that it is.
Yeah. Okay. There's no friction on the block.
Okay.
Okay, we'll put it that way. It's like on a, it's got an air thing or
How do you
something.
hold on to it then?
Oh, I didn't say there was no friction on the top of the block, just between the block and the ramp.
Oh.
Quit poking holes in my story. Okay, so here's why they do the same amount of work. The only type of energy being changed about the block, assuming we move it up the ramp at a constant velocity and lift it at a constant velocity, is the potential energy. If the blocks have the same mass, both blocks are on Earth, and they're going to the top of the same ramp, are all three of those numbers the same? Doesn't matter how I get something to the top of the ramp, I do the same amount of work because I change the energy of the object by the same amount. This is the whole reason we designed ramps. Okay? The inclined plane is like the simplest machine. Machines don't make less work. They make work easier. Okay? A ramp makes work easier because this amount of work has to be done by a force over a distance. If I lift this rock to the top of this ramp, the distance is small, but the force required is quite great. Okay? If I place that block on the ramp, does the ramp support a lot of the block's weight? Does that mean I exert less force? But I have to exert that smaller force over a greater distance. So I do the same amount of work, whether I use the ramp or whether I lift the rock to the top. Okay? That's how the Egyptians built the pyramids. They didn't have help from aliens. Okay? They had sand that they could make ramps out of, and lots of people to move the rocks. Okay? Incidentally, apparently they weren't all slaves. Apparently it was a great honor to work on the pyramids. Okay? So much so that you got buried in them, whether you were dead or not.
Yeah, because the aliens didn't want anybody to know about them.
Right. Yes. It's a conspiracy, right?
It's
Okay.
fact.
So does that make sense? Okay. Why these two people would do the same amount of work? Okay. It just goes back to the definition of work. That work is a change in mechanical energy. Since both rocks have their energy changed by the same amount of work is done. Okay? Less force, greater distance, more force, shorter distance. Okay? Okay, in this situation here, with the pulley and the two masses, okay? So if I lift this, or if I pull back on this block, assuming this table is frictionless, okay? Do I give the whole system energy? I do. Okay? All that energy, though, is in what form? Potential. And it's actually only in one part of the system, isn't it? Because the block is sitting on the table. It can't fall. Only the ball can fall. Okay?
That's
So,
right.
yeah. Okay? So only the ball actually has potential energy. But because the ball is connected to the block, the system has potential energy. Now, when the ball falls, is it going to fall at 9.81? Okay, why not? You're right, why not?
There's already 3 grams or kilograms of force that's trying to pull it back.
Right, it's actually not force, but mass. Okay, it's got to pull this other block along with it. Okay, the energy of this ball is m times g times h. But once the system gets moving, it's not just the 5 kilograms that's moving, it's 8. So the rate of acceleration will be reduced, but the energy will be conserved. It will just be in 2 places. The block will have some energy, kinetic, because it'll be moving, okay? And the ball will have some energy, kinetic, because it'll be moving, okay? But it'll be split. Not necessarily evenly, because the masses aren't equal, okay? But it will be split. Okay? But the whole system retains that amount of energy. Is that all right with everybody? We use that all the time, okay, in simple machines. We use the energy of one part of the system to do work in another. Okay? All right. Okay, so we talked about this, okay? M times G times H calculates potential energy. Okay? M times G actually calculates the force of gravity. Okay? What we would also call weight. Okay? The force of gravity is your weight. So if M times G is the force of gravity, and I'm multiplying that by height, is that still this? Height's a vertical distance, right? So that formula is still force times distance. It's just the force of gravity times distance. Okay, what units do I get here? joules. Okay? Energy is always measured in joules. But a joule is not a fundamental unit. Okay? Joule is made of fundamental units. So what's my mass? My mass is going to be in kilograms. Whoa. Okay? Mass is going to be in kilograms times acceleration, which is in meters per second squared. And what's distance in? Meters. Okay, so this is going to be a kilogram meters squared per second squared. That is a joule. Aren't you glad we call it joules?
Yeah.
Okay, do you still need to know what a joule is?
Yeah.
Yes. Okay, I'm like quite certain I will never ask you for that, but it's important that you know it. Okay, because if you're doing manipulations or solving a problem and you're solving for mass, you need to know you're getting mass in kilograms, and that you're getting acceleration in meters per second squared or distance in meters. Okay, so if a question was to give you distance in centimeters, you would have to convert it to meters. You can't put centimeters in a work energy theorem calculation because it won't give you joules. Joules are a kilogram meter squared per second squared. Okay? You always have to make sure your units are right. Same with mass. If you get the mass in grams, you got to convert it to kilograms. Okay? All right. So if we're looking at this, let's say we've got a 3 kilogram box lifted by an upward force 1.50 meters above the surface of the earth to the top of a table. What is the potential energy of the box in its new position? All right, so I would simply use this formula. Okay, plug in my numbers. 3 kilograms times 9.81 times 1.5 meters. It would now have 44.1 joules of potential energy. How much work was done? Box was on the ground. I lifted it 1.5 meters. Now it has 44.1 joules of energy. How much work did they do? What's the definition of work? No, that's the formula. What's the definition? How much did I change the energy by? 44.1 joules. Okay, it started on the ground. It had no energy. Now it has 44.1 joules of energy. That means I did 44.1 joules worth of work. Okay, I've done that 3 times now, guys, today. Okay, or I've gone back to this definition of work. Work is a change in energy. Work is a change in energy. How important is that? That is the work energy theorem. Work is a change in mechanical energy. And it's going to come up over and over and over again. And we're going to have to apply it to situations like this. Okay. Another way, we could have to manipulate it and be asked to find height when we're given the energy of something. So, okay, we have a 55 kilogram diver standing on a platform. Okay, on the top of that platform, they have 5.40, that's supposed to be 10 to the 3, okay, joules worth of energy. Okay, so we're looking for the vertical height of the platform. So our givens are, we have EP, okay, 5.4 times 10 to the 3 joules. Okay, we have the mass, 55 kilograms, and we have G. What's G? Right, 9.81 meters per second squared. Okay, so if this formula calculates potential energy, can I manipulate it for H? Yeah, I just have to take mg and do what with it? Divide it over to the other side, right? If I'm multiplying all 3 things, it's an easy formula to manipulate. Just divide the other 2 over, okay? And I'll have 5,400 joules divided by, in brackets on the bottom, okay? Those 2 numbers, and that will tell me that that person is standing on the 10-meter diving platform. Okay. Pretty straightforward. So how much work did that person have to do in climbing the stairs to the platform? How much energy did they have when they were standing on the platform? 5,400 joules. How much work did they do in climbing the stairs to the platform? 5,400 joules. Okay? Bottom of the platform would be ground level. How much potential energy would they have there? 0. Okay? So they would have to exert a force through a distance in climbing the ladder or climbing the stairs to the top of that platform. Then doing 5,400 joules worth of work. Okay? That's the fourth time now, guys. Okay. Okay, I'm going to give you a little break here, maybe about 5 minutes before we start talking about kinetic energy. Okay, let's talk about kinetic energy here, because kinetic energy is the type of energy that gets work done. Okay? Moving objects can do work. Stationary objects can't. Okay? So having potential energy is all well and good, but it has to be converted into something that can actually cause change. Okay? So that could be simple, like swinging a hammer. Okay? Or having steam turn a turbine. That's how we generate the vast majority of our electricity in Alberta. Okay? We burn fossil fuels and then we evaporate water and the steam turns a turbine. Or we have wind farms where wind turns a turbine. Okay? Either way, we've got molecules that are moving, okay, and they're causing a mechanical change in something else. Okay? And moving molecules in a sound wave can make your eardrum vibrate. Right? So if you're listening to your headphones, okay, and they're putting out sound, your eardrum is vibrating back and forth, okay, because the sound waves, which are moving the molecules of air in your ear canal, okay, are causing your eardrum to move.
It's crazy that your brain can like differentiate between so many different sound waves so quickly.
It's crazy that your eardrum can vibrate to that many different sounds, okay, all at the same time. Right? You think about when you're listening to music, how many different frequencies of sound are hitting your eardrum at the same
And
time.
then you can hear somebody talk to you while you're listening to music.
You can?
Yeah.
How come my kid never answers me then?
Oh no, I can't like answer. Like I can hear it, but I don't listen.
I don't think he answers. Yeah, I don't think he hears me.
Yeah, and then my left ear is that my ear just can't, my left ear only can't differentiate the different sound waves.
Just that they're there.
Yeah,
Yeah.
so they're still there, just
Right.
can't differentiate.
Is it a bone thing or
It's a nerve thing.
is it a nerve thing? Okay. Yeah, because there's lots of different reasons for having hearing loss, which is a good thing to bring up here, guys. Okay? Lots of different things can cause hearing loss. Your generation is probably going to have some of the worst geriatric hearing problems of any generation before you.
All right.
Okay? Because you have transportable music with you all the time. Okay? I don't know, like I walk around the hallways, even sometimes in class, people got their earbuds in when they shouldn't, but okay, they've got their earbuds in all the time. You're always listening to music. Now, if you have, okay, earbuds that can go beyond 90 decibels,
Oh, mine. I've seen mine hit 110.
okay, they can cause permanent hearing damage.
Yeah.
Any sound over 90 decibels is starting to permanently damage your hearing.
Every time it's a
Okay.
notification pops up, like your sound's too loud.
I should.
And it
Or
automatically
like
turns it down.
when you get it into the red zone.
Yep. Okay, so you have to be careful of that.
I should check how the decibels my truck is because I straight my.
Yeah, so you're like the guy that drives by my house, the rolling
No,
rate?
mine still has a muffler. Sounds good. It's just loud.
Okay.
Like it's not like.
It's a custom exhaust or what you do.
Oh yeah, it's a custom exhaust.
But that's why there's so many now workplace safety things, right? Where if you're in a workplace that's loud, you have to have ear protection, okay? Things like that, are trying to save your hearing versus every day you put the earbuds in at 100 decibels, okay, and cause hearing damage. Now, here's how that works though, okay? The energy of those sound waves are hitting your eardrum, okay? And the eardrum is connected to 3 little bones, okay, in the middle ear, okay? The hammer, anvil, and the stirrup, okay? Now, those little bones are connected by ligaments in the same way that your ankle and knee and shoulders and wrists are. Okay? When bones are connected, there's connective tissue between them. Okay? Ligaments, cartilage, tendons, things like that. These are tiny because these bones are tiny.
Oh, so they
Right?
rip easy.
Well, it's not as much as they rip. I mean, if you tore your eardrum, yeah, you'd be in real trouble. Okay, but like any other joint, if you make them move too much, you cause a sprain. Okay, so if you've ever twisted your ankle, you know that after it's swelled up. Okay, it was probably tender for a couple of days. You ever had ringing ears? Okay, ringing ears are evidence of swelling and inflammation in the ear.
Wait, really?
Yes, if your ears are ringing, it is because there's inflammation in there.
Really?
Yes, really.
No way.
I am not kidding you.
Yeah, 'cause my
Okay,
ears are
so,
ringing right now.
yes, you're ringing right now. Okay, like if you go to a concert or you go to a Flames game and maybe they actually score a bunch of goals and, you know, so the siren goes off a whole bunch of times. I know that hasn't happened
Yeah.
recently, but, okay.
Like a 41st Street.
So when that happens, okay, you get that loud burst of sound or even sustained sound for quite a while, okay, that makes your eardrum move a little more than it should, okay, which can injure those bones a little bit. Okay, now of course you're going to be exposed to loud sounds here and there. Okay, the odd loud sounds not a big deal, but being continuously exposed to those loud sounds is like continuously rolling your ankle. It's just going to get weak. Okay, and the same thing happens. You get scar tissue in that joint. Well, you get scar tissue in the ear. Okay, and that scar tissue then starts to reduce the flexibility and movement of those bones, which then starts to narrow the range of your hearing.
That actually explains a lot, because my earbuds used to sound like really loud at half volume. Now I crank those suckers and I can barely hear it.
Okay, there you go. All right, so you gotta be careful. You want to hear your children laugh.
You do?
Yeah, it's a pretty cool sound, especially when they're small. Later, when they're older and they're laughing at you, it's not as fun. Okay, but yeah, when they're little,
You can hear them laugh, you can hear them cry though.
yes, but the crying you can fix usually. Okay,
You wouldn't
so
think
does that sort of make sense?
Fix the laughing.
Okay, it's still a work energy theorem thing, guys. Sounds that are loud are exerting a lot of force. They have a lot of energy. Okay, thus they can do a lot of work. And we have to be careful of them. If you're listening, if you hear a sound that's 130, this scale is logarithmic, by the way, so
Yeah,
it's
I
not
think every
linear.
10 decibels, it's 10 times as loud.
Yeah.
Yeah.
So at 130, you instantly perforate your eardrum. Okay, when the flames score or you're at a concert, it's about 110.
So that's
It's pretty loud.
So that's 100 times louder.
Yeah, than 90. Okay, to give you an idea, 60 decibels is about what the inside of a car on the highway is. So if you're just sitting in the car, the sounds of the car are about 60 decibels. Right now, my voice is about 65 or 70. Okay, average conversation.
Yeah, no, my truck
Okay.
is much louder.
Yeah, much louder than that. Yeah. Okay, so kinetic energy can do work, and kinetic energy is based on only two things. What two things do you suppose would influence how much kinetic energy you have? Okay, if you're converting it to kinetic, yes. I'm actually thinking like if I had a formula that calculated kinetic energy, what two things would be in it? One of them's in the potential energy formula. Mass. Okay? And what else?
Work.
Well, work would influence this. So again, same argument as the potential energy. Yes, how much work I do does influence, but if I'm looking at two things that would be part of the formula, what two things would be in it? Velocity. Okay, M and V. Now, the formula actually looks like this. Kinetic energy is 1/2 times M times speed squared. Okay? So here's what that means for kinetic energy. It has an exponential relationship with speed. So, if I've got an object moving towards me at 1 meter per second, it has a certain amount of kinetic energy. That same object moves towards me at 2 meters per second, it doesn't have twice as much energy,
4 times.
4 times as much energy. If that same object moves towards me at 3 meters per second, now it's going 3 times faster, it has 9 times as much energy. Okay? It's an exponential relationship. Okay? Now, that means that the faster you go, the more work you can do, which is why school zones, playground zones, okay, construction zones all have reduced speed limits, and in some cases, more severe penalties.
Yeah, 2 times when workers are present.
When workers are present, your fines will double. Okay, they should do the same thing in a school zone and a playground zone, in my opinion.
Yeah.
They don't. So the reason for that is that if you're going more than 30 kilometers an hour, you have way more ability to do work, and it will require far more distance for you to what?
Stop.
Right. Okay, so this is what it comes down to. Work energy theorem is the reason we have speed limits the way we do. Work is force times distance. Okay? That means forces exerted can cause changes in kinetic energy. Agreed? Okay, so let's say I'm driving through a playground zone, kid runs out in front of me. Okay? I slam on the brakes and come to a stop before hitting the kid. That's the key part. Okay? What's my final kinetic energy? I came to a stop. What's my final kinetic energy? 0. Okay. So my initial kinetic energy then is one half times the mass of my vehicle times the speed my vehicle is traveling squared. Okay? The stuff on this side has to do with taking that energy away. In order for me to stop, I have to convert my kinetic energy into other forms of energy that don't equal moving. Okay? So I use the force of friction, that's what this force is, my braking force. And the D is how long it takes me to stop. Okay? Everybody with me on that? All right. So would it be possible for me to figure out how far I would travel before I stop? All right, let's say I'm in a 2,000 kilogram vehicle. Okay? And I'm traveling the speed limit in a playground zone. So that would be 8.3 meters per second. That's 30 kilometers per hour in meters per second. Okay? 8.3 meters per second. It's actually 8.3 repeating. Okay? Let's say that my brakes can exert 9,500 newtons worth of force stopping me. Do I have everything except D at this point? Okay, so then I can calculate what D is, yes? All right, what do I do with F? Divide it over to the other side. Okay, so 1/2 times 2,000 times 8.3 repeating squared divided by 9,500 newtons worth of braking force. Okay, so 0.5 times 2,000 times 8.3 squared, okay, divided by 9,500 newtons. All right, so my car will stop after 7.3 meters.
That's really good.
It's a long way when a kid runs out in front of you. And that's going the speed limit. Okay? Probably my brakes have more force than that. I just kind of picked the number out of my head. Okay? Probably it's more like
And if you
15.
pump them when you're going 4 kilometers an hour.
Well, you mean your anti-lock system would hopefully kick in and stop you quickly. Okay? But probably my brakes would be exerting more like 15,000 newtons worth of force. I just kind of picked that number there. All right. So that's at the speed limit. Now, what if
Just toss them.
the person going through the playground zone is a complete idiot and they're going 60? How much farther are they going to travel before they stop?
Exponentially.
exponentially further. They're going twice as fast. They're going to go
4 times.
4 times further. It's an exponential relationship. If I double my speed, I'm going to travel twice, not twice as far, 4 times as far, because I will have 4 times as much energy that I have to get rid of. Okay, so if I do this, it was instead 16.6 as my speed, so double my speed. Okay, so 0.5 times 2,000 kilograms, same vehicle. Okay, times now 16.6 repeating, squared. And then divide that by my braking force. Yeah,
That kid's
that's
done.
4 times. Yeah, 30 meters, that's 1/3 of one of the straight sides of the running track out back. Okay, that's why you don't go 60 through a playground zone. Okay,
During school hours.
After school hours.
Playground
so
zone.
playgrounds are 7:30 to 1 hour after sunset. So during those hours, or basically any other time, okay? I mean, you gotta be extra careful, right? School zones, same thing, okay? I mean, there's little kids there, right? And there's a reason why the playground sign is a kid chasing a ball in the street, okay? Doesn't matter how many times you tell your kid, look both ways before you cross the street, your kid will reliably do that if you're lucky half the time. Okay, take it from a parent, reliably half the time.
I've never
okay?
looked both ways once.
Yeah, it's terrible, okay? That's why we have speed limits. They protect the vulnerable from physics.
Probably like 5 or 6.
Because you can't change this, okay? You cannot change the physics of this. This is what happens. Now, here's the thing that we all do, unfortunately, guys.
We should put like sofas on the front of cars that like if it hits them, you're sitting on the sofa.
So here's what happens. And people do this all the time. I will say myself included sometimes. It's not a big deal if I just go 10 kilometers an hour over. If I go 40, that's not that big a deal, right? If I go 60 in a 50 zone, it's not that big a deal. 120 in a 110 zone, it's not that big a deal. It's only 10 kilometers an hour. It's not that big a deal. Except that the relationship between speed and stopping distance isn't linear, it's
Exponential.
okay. So if I go 40 kilometers per hour, I'm just going to get it in meters per second here. That's 11.1 meters per second. Okay, let's do that calculation again. 0.5 times the car's mass times this number squared divided by my braking force. So I went from 7.3 to 13. I only went 10 kilometers an hour faster. That's only 25%. But my stopping distance is almost double. It's an exponential relationship. Here's the worst part of this. That extra bit of speed, okay, so if I go through this playground zones are on average about 400 meters in length. Okay, so if I go 400 meters, whoop, not 4,000, divided by the actual speed limit, it'll take me 48 seconds to get through that school zone or that playground zone. I saved 12 seconds.
My number was exact.
So, when you make the decision to go through the playground zone at 10 kilometers an hour over the speed limit, knowingly doubling your stopping distance, you are saying that that little kid's life is worth less than your 12 seconds.
I also feel like
Physics can be cruel. This is one of the days where physics is cruel. Okay? And guys, here's the thing in Okotoks. The light timing in this town sucks. You are going to hit a red light anyway. Whether you went through that 12 seconds faster or not, you're going to be stopped at the same stoplight.
unless you want to be airline.
Okay? Unless you run red lights, which means you're already a despicable person. So, okay? That 12 seconds, guys, is the difference between somebody having dinner with their kid tonight or planning their funeral.
That's really sad.
But it's reality. I say that because you guys are going to be new drivers, or maybe you already are. Okay? There are speed limits for a reason, especially in playgrounds, schools, and construction zones. People are vulnerable there. And your car, listening please, hey, your car is a deadly weapon. That's why you can be charged with assault with a deadly weapon if you hit somebody with your car.
My truck's real slow.
Okay?